Kia ora, Year 10. Here are the first 4 relational questions from the JAF practice worksheet. So these are all a mix of circle geometry and triangle problems and parallel line stuff. I'm going to save the polygons until later on this week. Okay, so here's the first one. The main thing we've got to do is show our reasoning at each step, and I do that using the shorthands that I've taught you in class. It's fine though if you want to write out the whole reason. There's nothing wrong with doing that, it's just a little bit slower. So let's look at 2a. We've got a circle, and we can see the point O is the centre of the circle. So as soon as we see that, we should think, well, that means that AD is a diameter, and that means that I've got a semicircle, and that this angle here is 90 degrees. So we can say that straight up. We can say angle AHD is 90 degrees, and my reason for that is the angle in a semicircle is equal to 90 degrees. So there's your first reason. Now, what can I do next? Well, I've got a triangle, so I'm going to use angles in a triangle. So 50 plus 90 is equal to 140 degrees. So F plus 140 degrees is equal to 180 degrees. So F equals 40 degrees. And the reason for that is that angles in a triangle equal 180 degrees. Okay, on to the second question, 2b. This is very much a Year 9 problem. The thing we want from you this year is we want you to very clearly explain your reasoning. So there are several ways to do this, but I'm going to start by saying that this angle here, angle LMN, is also equal to G. And the reason for that is that I've got an isos triangle, and the base angles in an isos triangle are equal. So there's my first reason. The next thing I'm going to use is the fact that angles in a triangle add to 180. So 180 minus 64 degrees is equal to 116 degrees. So 2G must equal 116 degrees. And my reason for that is angles in triangle equal 180 degrees. So just notice that I've used both this reason and this reason. It's not enough just to say the base angles in an isos triangle are equal, because we also have to use the 180 degrees property. I'm not quite finished. I've got 2G as 116, so that gives me G is equal to half of that, which is 58 degrees. So that's my final answer for that one. Okay, let's look at C and D. So question C is one where there's a very fast way to do it, if you remember the rule about the exterior angle. So the exterior angle outside a triangle can be found by just adding up the interior opposite angles. So we can go pretty much straight to the answer with this. H is equal to 50 degrees plus 74 degrees, which is equal to 124 degrees. And my reason here is the exterior angles, I keep saying this wrong, it's the exterior angle around a triangle is equal to the sum of the interior opposite angles. So that's one reason for that one. Now the other way we can do that one, if we don't remember the exterior angle reason, is that first we can find this angle here by using the property that angles add to 180, and then we can find this one by using the property that angles on a line equal 180. But I think it's good to get really used to using the exterior angle rule, because it's a very, very useful one that we come across quite often. Now the next question is the only one in this video that uses parallel line rules. You can see that these arrowheads are telling you that UT and VS are parallel. And once you see that, this question becomes pretty straightforward, because we know that if this angle is 73, this one must also be 73. So angle TUR is equal to 73 degrees, and that's because corresponding angles on parallel lines are equal. So that's reason number one. Now we're going to use the triangle 180 degree property to find W. So 73 degrees plus 34 degrees adds up to 170 degrees. So W is equal to 180 minus 107 degrees, which is 73 degrees. Whoops. Let's just fix that up. And I have to give my reason for that, and it's angles in a triangle add up to 180 degrees. So here's reason number 2. Oh, why is that not going into a nice rectangular box? I don't know, but it's not. Now just one thing on this. What we've also done in this question is that we started with just a triangle, and we've ended up showing that RUT is isosceles, right? Because we've shown that this is 73, and we've shown that this one's 73. So we could have been asked here to prove that triangle RUT is isosceles, and this is an example of working backwards with our rules. So when we start out in Year 9 by learning these rules, we learn how to find the angles. But often at Year 10 and 11, we show that if the angles are such and such, then this means that we've got an isos triangle. For example, if we had this, and we did some work, and we found that this was 58 degrees, and this was also 58 degrees, we'd say because the base angles are equal, we've got an isosceles triangle. And there are a couple of other places we've done that in this topic. One of them is when we were looking at parallel lines. So if I told you that this one was 80 degrees, and this line was, sorry, this angle was 100 degrees, we could say that these lines are parallel because the co-interior angles add up to 180. Or, if instead we had this one was 110 degrees, and this one was, I don't know, 72 degrees, we'd say that those two lines are not parallel because the co-interior angles do not add to 180, or in other words, are not supplementary. So we're working backwards, and I'm just going to do one last example of this because students tend to forget about this, but it's a really useful property. If we're doing a triangle question, if we're given the right angle, then we know that we can apply Pythagoras Theorem, right? A squared plus b squared equals c squared. So if I tell you that this side length is 8 and this side length is 6, you can go and do your thing and you'll find out that this side length here is 10. But this works the other way around as well. So if this side length is 8 and this side length is 5 and this side length is 10, we can show that this is not a right angle. And we do it like this. We say 5 squared plus 8 squared is equal to 25 plus 64, which is 89, which is not equal to 10 squared. So since a squared plus b squared is not equal to c squared, this isn't a right angled triangle. Okay, and we call this method of working backwards using the converse of Pythagoras, or up here the converse of the parallel line rules, or here the converse of the triangle properties. Alright, sorry, got slightly sidetracked, but hopefully that was useful. I'll do another relational video probably tomorrow or Tuesday night.